Alright, the compound angle formulas. I'm going to create them. There's different ways of creating these formulas. This is just one way. So what we do is we have a look at the unit circle. Of course, we have a point which I could find the x value and the y value. That angle there, let's say it's beta. With a little bit of trig, I can show that the x value of that point would be the cosine of beta, and the y value of that point would be the sine of beta. And it doesn't matter where I put it on the circle, it'll always be that. They're, if you like, the parametric equations for a circle. So of course I could put one over there, and let's say that angle's alpha, and that would be cos alpha sine alpha. Now, you might look at that and think, well, hang on, how can these be positive when clearly we can have a look and we see that the x value is negative, but of course alpha is obtuse. The cosine of an obtuse angle would be negative. So we do get a negative number. Alright, what I'm interested in looking at then is the distance between P and Q. I could do that a couple of ways. I could do it using trig, using our cosine rule. And we get PQ squared is equal to all of that, tidying it up. That's 2 minus 2 cos alpha minus beta. But I could also do it using coordinate geometry and our distance formula. And play around with that one. You've got a couple of cos squareds and sine squareds there, which we know they add together to give 1. And I get this expression. So now I've got two different expressions for PQ squared. Well, they've got to be equal because they're both PQ squared. So if they're equal, let's play around with that, and we get the first of our compound angle formulas. The cosine of alpha minus beta is cos alpha cos beta plus sine alpha sine beta. I'm going to play around with that expression. If I replace beta with negative beta, so I now get a formula for cos of alpha plus beta. But I'm not going to leave it like that because I know that cosine is an even function, and I know sine is an odd function. So I can rewrite that one. Very similar formulas. But what you'll notice is when it was negative here, it's positive on the right hand side, and when it's positive here, it's negative on the right hand side. So I could write it like that. Of course, the way I tend to remember it's like this. I just simply say, oh well, cosine, that's cos, cos, sine, sine. Because you've got cos, cos, sine, sine. Cos, cos, sine, sine, but if it's not the sine, and it's not the sine ratio, it's the cosine ratio. So no, it's not the sine. If it's not the sine, then it's not the sine. We change the sign. Okay? So there's your formula for the cosine. Cos, cos, sine, sine. If it's not the sine, it's not the sine. Alright, now I'm going to play around with it again. I'm going to replace alpha with 90 minus alpha this time. So I end up with this expression. But of course, cos of 90 minus alpha is the sine of alpha. They're complementary ratios. And I can now get a formula for the sine of alpha plus beta. We get the sine of alpha cos of beta plus cos of alpha sine of beta. And again, now I'll play around with that one. Replace beta with minus beta, and making the use of odd and even functions. Again, we get two very similar formulas. But you'll notice this time, when it's plus on the left-hand side, it is plus on the right-hand side, and so on. So, the way I could remember this one then is sine, cos, cos, sine. Sine, cos, cos, sine. If it is the sine, and it is, then it is the sine. So, cos, cos, sine, sine. If it's not the sine, it's not the sine. And sine, cos, cos, sine. If it's the sine, it's the sine. How do I remember those? Well, you always start with the same thing. So when it was cos, I started with cos. And whenever you say cos, it's cos, cos. So if I remember that for the cos one, then I go, well, okay, it's cos, so I start with cos, but hang on, whenever I say cos, cos. So it's cos, cos, sine, sine. If it's not a sine, it's not a sine. Whereas with sine, I'll start with sine, but then I'll go to cos. Oh, whenever I say cos. So it's cos, cos, sine. It's just the way my mind works. It could be a dangerous thing. Let's find one for tan. The tan of alpha plus beta, but of course we know tan is sine on cos. I can now substitute in what we now know, so the sine, cos, cos, sine. If it's a sine, it's a sine. And on the bottom of the fraction I've got cos, cos, sine, sine. If it's not the sine, it's not the sine. Let's simplify this by making it look more complicated. Right? I'm going to divide everything by cos, cos. But of course now there's all this cancelling that happens. See, the cos of beta will cancel with the cos of beta in that one, cos of alpha will cancel with the cos of alpha in that one, but of course what I'm left with is sine on cos, which is tan, and look what we get. Tan of alpha plus beta, which is tan plus tan on 1 minus tan tan. So tan plus tan on 1 minus tan tan. Let's replace beta with minus beta. Tan is an odd function, so therefore we get that one. Now, so with these ones, I just think of it as tan plus tan on 1 minus tan tan, but I just know that, well, if it's minus, then I'll just swap those signs around. But I still think of it as tan plus tan on 1 minus tan tan. So there's your 3 compound angle formulas. Let's play. So now if I expand this out, so why do we do this? You see, it's not like I'm expanding parentheses and I can say, well, it's cos 2 alpha minus cos 3 beta. It's not algebra we're playing with like that. We need these formulas to expand that out. So cos is cos, cos, sine, sine. If it's not the sine, it's not the sine. There's our answer. Cos 2 alpha, cos 3 beta, plus sine 2 alpha, sine 3 beta. If I had to simplify this expression, but what I notice, look at the form of it. Hang on, it's tan plus tan on 1 minus tan tan. Therefore, that's tan of 20 plus 10, tan of 30, which we know is 1 on root 3. If I had to find the exact value of sine 15, how do I get 15 from the exact values that I know? Well, there's different ways I could do it. I could go 60 minus 45. I could do 45 minus 30. There's different ways I could do it. Which way did I go? I went 45 minus 30. So it's sine, which is sine cos, cos sine. If it's the sine, it's the sine. I know those exact values, and there's the exact value now for the sine of 15. Root 3 minus 1 over 2 root 2. If the sine of alpha is 2/3 and the cosine of beta is 1/4, what is the sine of alpha plus beta? Draw myself up a little triangle so I can get the other side, which is root 5, and now do the other triangle, because remember, alpha and beta are not necessarily in the same triangle, and in this case they definitely are not in the same triangle. I have one for alpha, one for beta. And then we just substitute in sine. Sine, cos, cos, sine. If it's a sine, it's a sine. Substitute in, got our answer. Ooh, the tan of the inverse sine of 2/3 plus the inverse cos of 1/4. Remember, inverse sine, inverse cos, they are angles we're actually talking about. So this is tan of alpha plus beta. To make life easier, I might actually say that. Alpha is the inverse sine of 2/3. Draw myself up the triangle, and the other side will be root 5. Beta is the inverse cos of 1/4. So draw that triangle up. But what I've now got is tan plus tan on 1 minus tan tan. Sub in, playing around with it, and eventually, there we go, 2 plus 5 root 3 over root 5 minus 2 root 15. Okay, so 17D will play with these compound angle formulas.